Okay, so, okay. Okay, so this is week 2, chapter 4. We're going to go through some fractions and mixed numbers. We should be able to get through sections 1 through 3, and we may start section 4. So if you want to unmute yourself and talk, that's fine. If not, you can just use the chat. I'll kind of keep it open on the side here and watch. Okay, so fractions. A fraction is something that is cut into equal portions. Those equal portions we call fractions of the whole. Fractions written in the form of A over B. A would be your numerator, B would be your denominator. A and B are whole numbers, which in this case, that should say are integers, because they could be positive or negative. Okay, would you rather me just record a lecture on my own and email it to you? Yeah. Okay, I'll go ahead and do that. I don't know what is wrong with the internet. I don't know, maybe Zoom is just, because I've had Zoom sessions before, but today I had a meeting earlier and I had some issues with it as well. Okay, so I'll just record a lecture on my own and I will send it to you. And if you have any questions, you can just email me tomorrow or Friday or over the weekend, okay? You're welcome. Bye-bye. Okay, so fractions A over B, where A and B in this case should be whole numbers. B is not equal to 0. A is called the numerator, B is called the denominator. The denominator represents the number of equal portions to which the whole unit is divided. The numerator represents the number of those equal pieces we have. So we have this circle here. If we cut it into 3 equal pieces, then the denominator would be 3. 2 of the pieces are shaded, so we would say 2 out of the 3, or 2/3 of the circle, is shaded. 1 piece is not shaded, so we would say 1 out of the 3, or 1/3, is not shaded. So some properties. If your fraction has a denominator of 1, it is equal to the numerator. So it would be the whole number. If you have 2 over 1, your fraction is equal to 2. Because if you have a whole unit and it's not divided into equal portions, if it remains the one whole unit, and you have 3 of those such units, 3 over 1, that means you have 3 whole units. A fraction whose numerator is 0 is equal to 0. Because if you have a pizza cut into 5 slices, but you don't eat any of those slices, you've eaten 0 pizza. If the denominator is 0, your entire fraction is undefined, because a whole unit could not be separated into 0 equal portions. If we do not separate it, it is still 1 whole unit. That's where the denominator of 1 came in. So if there's a denominator of 0, the entire fraction is equal to undefined. It's not equal to 0, it's undefined. If your numerator and denominator are the same, if you have a pizza cut into 8 slices and you eat all 8 slices, you've eaten 1 whole pizza. So if the numerator and denominator are the same, your fraction is equal to 1. If your numerator and denominator are both negative, the fraction is actually positive. Because remember, a fraction is a division problem. And a negative divided by a negative would be positive. So -1 over -2 would be positive 1/2. If the fraction is negative, the negative sign can be associated either with the numerator or the denominator, right? It can't be both because then it would be positive. So if your fraction is negative, this negative sign either goes with the top or with the bottom. So what we usually do is leave the negative out front and understand that it is either the top or the bottom part that is negative, but not both. Okay, so difference between proper and improper fractions. So a proper fraction is a fraction whose value is less than 1. So the numerator would be smaller than the denominator. 2/3, 3/4, 5/7, any fraction whose numerator is smaller is called a proper fraction. The denominator, or a fraction whose value is greater than 1, is called an improper fraction because it means that a fraction whose numerator is greater than the denominator is called an improper fraction. Because if the numerator is bigger than the denominator, this means the fraction represents more than a whole unit. So for example, 4/3, we have 2 circles cut into 3 equal pieces. Well, if we have 4 out of those 3 equal pieces, that means we have a whole and part of another. So an improper fraction, the value is greater than 1, and the numerator would be bigger than the denominator. So an improper fraction, remember, is greater than 1. We can also represent an improper fraction as a mixed number. Mixed number is another way to write an improper fraction, to show a value more than 1. So a mixed number is actually a sum of 2 numbers. It's the sum of a whole number and a fraction, but we don't put the plus sign between them. It's understood that this means a whole pizza and a third of another pizza. So if your mixed number is negative, then both of those pieces are negative. If you were to show it as a sum, it would be a -1 and a -1/3. Both parts, both the whole number portion and the fraction portion, are negative. So changing a mixed number to an improper fraction, you multiply the whole number by the denominator and then add the numerator. So the denominator times the whole number plus the numerator. 3 times 2 plus 1 would give us 7. And then we keep the denominator the same. So when I learned how to do this, we called this a backward C. You start at the 3 and go around to the top. So it'd be this 1 1/3 would be 3 times 1, which is 3, plus 1, which is 4. 3 times 1 plus 1. And then we keep the denominator the same. So we'd have 3 plus 1, which is 4/3. So notice we have 1, 2, 3, 4 thirds. So if your mixed number is negative, remember both portions are negative, but when you're changing it to an improper fraction, you keep the sign separate. Okay, so don't assume that you're multiplying a negative times a negative here. Pull the negative out, forget about it for a minute, and then you would just take 5 times 2 plus 1, which is 11 over 5, and then put your negative back in. Okay, so the fraction 7/3 means we have 7 parts of a circle where each part is a third of the circle. So every 3 of those thirds makes a whole circle. So 3 thirds and 3 more thirds, that would be 6 thirds, plus this 1 third, that's 7 thirds. So these 2 3/3 pieces each represents a whole. So that would be 2 whole and 1/3 of another. So a mixed number or an improper fraction can be changed to a mixed number by division. We divide the numerator by the denominator, or you can think of it as dividing the denominator into the numerator. Do our subtraction, and then the remainder becomes the numerator of the fractional portion of our mixed number. So 7/3, 3 goes into 7 twice. 2 times 3 is 6. We subtract, we have 1 left over. So our mixed number is going to be 2 whole units, then 1 out of the 3 left. So the top number is your whole number, the remainder is your numerator, and again, the denominator does not change, right? Our denominator was 3 to begin with, and it's 3 at the end. So rewrite as a mixed number. So let me pull up this. And we'll go through these one by one. So 17 over 5. So that is 5 going into 17. 5 goes into 17 3 times because 3 times 5 is 15. Subtract, we have a remainder of 2. So that means my whole number is 3, my numerator is 2, and my denominator stays 5. So 17/5 is 3 2/5. 31/4, that's 4 into 31. 4 goes into 31, 8 would be too many, right? 4 times 8 is 32, so we'll go with 7. 7 times 4 is 28. Do our subtraction. 4 left over. So that means my whole number is 7, or 3 left over, sorry about that. My whole number is 7, my numerator is 3, and my denominator stays 4. So 31/4 is 7 3/4. Now we're going to take these mixed numbers and turn them to improper fractions. So we have 2 5/8. 8 times 2 plus 5 all over 8. 8 times 2 is 16, plus 5 is 21 over 8. So 2 5/8 is equal to the improper fraction 21/8. And the last one is 3 11/12. So we have 12 times 3 plus 11. 12 times 3 plus 11 all over 12. So 12 times 3 is 36, plus 11 is what? 47. So 47 over 12. So 3 11/12 is equal to 47 over 12. Okay, so fractions in the number line. Fractions, again, remember, represent parts of a whole. We can think of the spaces between our integers as whole units. And if we separate those spaces into equal portions, we can think of those as fractional portions of the whole units. So between 0 and 1, think of this as a whole unit. If we cut it into 2 pieces, each piece represents a half of the unit. So this piece is 1/2. This piece here is also a half. So this first mark represents half. Now, if we jump over to 1, this would be 2 halves, because this would be the space from 0 to 1. So from here to here is 1/2, but from here to here would be 2 halves. And remember, if your numerator and denominator are the same, you have 1. So 2 halves, or 2 over 2, is equal to 1. Go to another half, we have 3 halves. So the next step would be 4 halves, which reduces to 2 whole units. So notice the second line, each unit is cut into 3. So each mark would be another third. So we have 1/3, 2/3. This would then be 3/3, 4/3, 5/3, then 6/3 would be your 2. So here, to find our denominator, we need to count the number of units this 1 is separated into. So we have 1, 2, 3, 4. So each whole unit would be separated into 4 smaller units. This means each unit is 1/4. So the first would be 1/4, 2/4, 3/4, 4/4. So this circle would then be 5/4. And then the next mark would be 6/4. So looking at the next line, we have 1, 2, 3, 4, 5 smaller portions. So each of these is 1/5 of the whole. So we have 1/5, 2/5. This would then be 3/5, 4/5, 5/5 would be the 1, 6/5, 7/5, 8/5, so on and so forth. Okay, so we're talking integers and fractions. These fractions that are negative would then be on the other side of 0. So the number lines may look a little different because actually what I did was I took this number line and reversed it and added the negative to make these negatives. So the 1 looks backwards, but just understand this is to the left of the 0. So we're in the negative of the number line. So again, negative fractions are just like negative whole numbers. They're the opposite of your positive fractions. They're the same distance from 0 as your positive fractions. They're just in a different direction. So again, on the left of 0, if you separate the 1 unit into 2 different units, each of those smaller units is a half. So the first would be -1/2, the second would be -2/2, then -3/2. Our second line here is separated into thirds. So we would have -1/3, -2/3, -3/3 would be the -1, -4/3, -5/3, and keep on going. So this line here, the whole is separated into 1, 2, 3, 4. So each smaller is -1/4. So we had -1/4, -2/4, -3/4, -4/4 would be 1, -5/4 would be the circle. And our last number line again is separated into 5 smaller units. So each unit would be a fifth. -1/5, -2/5, -3/5 is the circle, -4/5, and -5/5. So again, absolute value means distance from 0. So whenever you throw absolute value bars around something, that something becomes positive. If it's already positive, it just stays positive. If it's negative, it becomes positive. Because again, absolute value represents distance. It doesn't care about direction. The sign is what tells you the direction. So it's basically saying disregard the sign. The distance from 0 to -3/2 is 3/2 units. The distance from 0 to -1/3 is just 1/3 of a unit. Okay, so 1 second. Okay, so simplifying fractions. When we simplify fractions, what we are actually doing is removing common factors. The reason you are able to divide a numerator and a denominator by the same number is because that number is a common factor to both the numerator and the denominator. The act of dividing the same number from the numerator and the denominator is in essence removing 1 from the fraction. Because remember, if the numerator and denominator are the same, your fraction is equal to 1. So if we have, say, the fraction 4/20, I'm able to remove a 4 from the top and a 4 from the bottom. What is the fraction 4/4? That's equal to 1. So in essence, I'm only removing 1 from the fraction. We can look at the 4 as 1 times 4, right? 4 is equal to 1 times 4, and I can look at the 20 as 5 times 4. So basically what I'm doing is creating a 1 out of these two 4s, or we call it canceling the 4s. The reason I can divide 4s out is because they're both a factor of the numerator and a denominator. So in essence, I'm canceling the common factors between the numerator and the denominator. So if we notice the number 10, 2 times 5 gives me 10. 2 and 5 are both factors of 10. So I could divide 2 out of 10 to get 5, or I could divide 5 out of 10 to get 2. So if my fraction had, say, a 10 in it, two tenths. Well, I know 2, or the 10, is made up of 2 times 5, and 2 is made up of 2 times 1. So 2 is a factor of 2. 2 is also a factor of 10. I can cancel it from the fraction and go from 2 tenths to 1/2. So that's the idea behind factoring. Factors are numbers that multiply to get other numbers, or you can think of them as numbers that divide out. But the reason they divide out is because they had to multiply to begin with. So, couple important things that's really going to help you reduce your fractions. First and foremost, know your multiplication tables. If you know your multiplication tables, you don't have to grab your calculator every time you're asked to reduce a fraction to test whether a number divides out of the top and bottom. So if you know your multiplication tables, it's going to be that much easier, and it's going to save that much time. If you have to grab your calculator every time you're asked to reduce a fraction, you're going to waste a lot of time. That's going to eat up your time, and you know your tests are all timed. So there's also divisibility rules that will help signify to you whether a number is divisible by another number. So any number is divisible by 2 if it's even. A whole number is divisible by 2 if it's an even number, right? Anytime there's an even number, you automatically know I could divide 2 out of it. Divisibility by 3. A whole number is divisible by 3 if the sum of its digits is divisible by 3. So the number 312, you wouldn't think right off the bat to divide 3 out. You would look at it and say, oh, that's even, let me divide 2 out. But in essence, 3 plus 1 plus 2 is 6, so that means it's divisible by 3 as well. Divisibility by 4, a number is divisible by 4 if the last 2 digits, the 10s and the 1s digit, make up a number that's divisible by 4. So if we look at 140, 40 is the number 40, and it's divisible by 4, therefore 140 is divisible by 4. Same with 916. 16 is the number 16, it's divisible by 4, so the entire number is divisible by 4. So any number that ends in 5 or 0 is divisible by 5. That's pretty common. Most people know that. Most people know the 2 and the 5 and the 10. But the 3 and 4 are not very common, And then the 6, you'll see it's divisible by 6 if, not 3 and 4, I'm sorry. 3 and 4 are uncommon, so it would help you to definitely memorize those. Divisibility by 6 is possible if it's divisible by both 2 and 3. So if your number is even and the digits also add up to something that's divisible by 3, then your number is also divisible by 6. So back here up at 312, it's even. We know it's divisible by 3, so I could have divided a 6 out of it as well. Divisibility by 9 if the sum of the digits is divisible by 9. And then if it ends in 0, it's divisible by 10. Okay, so the divisibility rules will help you. So you could be able to look at a number and decide, kind of right away, find something that it's divisible by. Like I said, the 2, the 5, the 0, those are pretty common. So 3 and 9, pretty much the same concept. If they add up to something that's divisible by 3, it's divisible by 3. If they add up to something that's divisible by 9, it's divisible by 9. So then 6, if it's divisible by both 2 and 3, so if it's even and they add up to something divisible by 3, and 4, if the last 2 digits are divisible by 4. Okay, so I mean, you don't have to remember all of them. I don't personally remember all of them. I usually check with 2s, 5, 0, and the 3 and the 4. I rarely ever remember the 6 and 9. But whatever helps, Okay, so prime factorization. So to write the factors of a number is called, is just writing the factor of numbers, the number as its factors. Prime factorization is a little bit different. We want to write the number as a multiplication problem, but multiplying all prime numbers. So if you remember what a prime number is a number whose only factors are 1 in itself. So the number 2 is prime, the number 3 is prime, number 5, 7, these are all prime numbers because the only things they're divisible by are themselves and 1. Now a number that is not prime is called composite. So 4 is composite because it's divisible by 1 in itself, but it's also divisible by 2. If you think about 6, it's composite. It's divisible by 1 and 6, but also 2 and 3. So prime factorization is writing a number as a product of prime numbers. So if we look at the number 72, first of all, if you notice, it's even, so I divide out a 2. I actually could have said, well, 7 plus 2 is 9, and 9 is divisible by 9, so I could have divided a 9 out right away. But I started with 2's. So 72 is 2 times 36, but 36 not prime, so I need to break that down. 36 is 2 times 18. 18's not prime. 18 is 2 times 9. 9 is not prime. 9 is 3 times 3. So in essence, 72 is 2 times 2 times 2 times 3 times 3. These are now all primes, so we have written 72 in its prime factored form. Now remember, repeated digits that are multiplied, we can replace the 3 2's with 2 to the 3rd power. We can replace the 2 3's with 3 to the 2nd power. So either way is correct. You can write it as just a product of single prime numbers, or you can shrink it up to their exponential forms. So maybe you've seen these in the past. We call these factorization trees. So it's basically a way of visually breaking down a number into its primes. So here, if you look at this blue box, this is from your book, the number 220. They broke it down first into 2 composite numbers, 4 and 55. Then you have to break the 4 down into its primes, same thing with 55. So the prime factorization would be 2 times 2 times 5 times 11, or you could have wrote 2 squared times 5 times 11. And there's many different ways to do this. So if you look at 220, if I start with 2's, it's 2 times 110, and then 2 is prime. So I won't have to break that down anymore, but the 110 is not. It's 2 times 55, and then 55 is 5 times 11. So then you see I have the primes 2, 2, 5, and 11, just like they did here. So either way you do it, you're going to have the same factorization. If we look at 36, I could use what? I could have used 2 and 18, or I could have used 6 and 6, or 3 and 12. I use 9 and 4, because 9 times 4 is 36. So then if I break the 9 down further, I get 3 and 3. If I break the 4 down, I get 2 and 2. And once you get to prime roots, you can call them. They kind of look like roots of the tree. Once you get to a prime, you're done. So 36 in prime factored form is 3 times 2 times 3 times 2, or 3 times 3 times 2 times 2, or 2 times 2 times 3 times 3, or 2 squared times 3 squared, or you could rewrite this as 3 squared times 2 squared. But it's still 2 2's and 2 3's. 360, 10 and 36. 10 breaks down to 2 and 5. Both of those are primed, so I stop. The 36 is 6 and 6, and then each of the 6's breaks down. So I have 1, 2, 3 2's, 2 3's, and a 5. And if I want to write them with exponents, 2 cubed times 3 squared times 5. So this is going to help you when you have to reduce fractions that contain not only numbers but variables. So equivalent fractions. Equivalent fractions are fractions that have the same value, but they look different. So if you look at the 3 circles, these are the 3 circles are the same size. They're just divided into more and more equal portions. So if I take one circle, just divide it into 2 equal portions, the second circle is divided into 4 equal portions. The third circle is 8 equal portions. But notice if I have one of the 2 portions, it's going to be the same as if I take 2 of the 4 portions, which is also the same as if I take 4 of the 8 portions. These 3 fractions are equivalent. They look different, but they represent the same amount of the whole. So one way to test if 2 fractions are equivalent is to see if their cross products are equivalent. So 1/2 is equal to 2/4. If I multiply the 2 and 2, I get 4. The 1 and 4, I get 4. 4 is equal to 4. Therefore, these 2 fractions are equivalent. So simplifying fractions to lowest terms. We kind of talked about it a little bit. We have to divide the same number out of the top and bottom. And we're able to do that because that number is a factor of both the top and bottom. And dividing the same factor out of the top and bottom is kind of taking a 1 out. So you're changing the look of the fraction, but you're not actually changing the value. Simplifying fractions is a method of creating equivalent fractions, right? If I take 4/8 and I divide top and bottom by 2, I get 2/4. If I take 2/4 and divide top and bottom by 2, I get 1/2. So simplifying fractions or reducing fractions creates equivalent fractions. So if we look at this fraction, -170 over 110, I could write it in its prime factored form. The 170 is 17 times 2 times 5. The 110 is 11 times 2 times 5. Cancel those common factors, right? Because 2 over 2 is 1, 5 over 5 is 1. And I get -17 over 11. So this is the same as dividing out a 2 and then dividing out a 5. I could also notice they both end in 0, so I could have divided out a 10 to begin with, or cancel that common factor of 10. 210 over 336. If I break them down to their prime factors, I notice 2s are common, 3s are common, 7s are common. So 210 over 336 reduces to 5/8. Now you can also do this with a drug concentration. If any of you are in the medical field, you may have seen concentrations printed on a label in 2 different ways. So you can have a drug label if we look at this drug label, this concentration, it's 5 milligrams per 5 milliliters, and below it, it also says 1 milligram per 1 milliliter. These are actually the same. One is the reduced form of the other. So here we have 25,000 micrograms per 1,000 milliliters. If we reduce this, we get 25 micrograms per 1 milliliter. So basically all we're doing is reducing by 10, 10, and 10, or think of it as dividing out 1,000. 25,000 over 1,000 is equal to 25 over 1. Just like 5 over 5, right? 5 milligrams over 5 milliliters is equal to 1 over 1, 1 milligram over 1 milliliter. So it works with variables as well, because variables, remember, represent numbers. So anything you can do to a number, you can do to a variable. It just may look a little bit different. So if we take 10x squared yz and we write it out kind of long ways, 10 is the prime factors of 2 and 5. X squared is xx, and then yz. And 15 is 3 times 5. Then we have x and 5 y's. So notice 2 5s. These are common in the top and bottom. We can cancel them. There's an x common in the top and bottom. We can cancel that. There's a y common in the top and bottom. We can cancel that. So on top, we're left with 2 times x times y, which is just written as 2xy, or z, I'm sorry, 2xz. On the bottom, we have 3 and 1, 2, 3, 4 y's. So I'm going to write it as 3y fourth, and then the negative stays. So basically, you reduce the 10 and 15 to 2/3. The x in the bottom canceled one of the x's in the top, right? So we got rid of the x on the bottom, and we got rid of one of the x's in the top. The y on top canceled one of the y's on the bottom, right? So there's no more y on top, and there's only 4 instead of 5 on the bottom. But we still have a z because there's nothing to cancel with it. So it works with variables, and it also works with unit abbreviations. And you'll see this when we get to conversions. So 25,000 micrograms over 1 times 1 milligram over 1,000 micrograms. So if we rewrite this numerator as one numerator, 25,000 micrograms times 1 milligram, the denominator rewrite as 1 times 1,000 micrograms, which is just 1,000 micrograms. Notice we can cancel all our zeros because those each represent 10, but we can also cancel this unit abbreviation. MCG means microgram. We can cancel the microgram on top with the microgram on the bottom. So then we end up with 25 milligrams. And this is actually a conversion. If I were to convert 20,000 micrograms to milligrams, 25,000 micrograms is 25 milligrams. And you'll see more of that when we get to dosage. So let's try reducing these. We have 170 over 102. Well, they're both even, so I know I can get a 2 out, right? So 170 is 2 times what? 80. 2 goes into there. 8. 2 times 85. But 85 then I know breaks down So that's 2 times, I know 5 goes into 85, what, 15 times? No, 17 times. So that's my top in prime factors. The bottom, 2 times 51, right? And 51, let's see, 3, yeah, 3 goes into 51. So 2 times 3 goes into 51, 17 times. So 170 over 102, cancel the 2's and the 17's, I end up with 5/3. 198 over 306. $198 over 306. So again, they're both even. I know I can get a 2 out. So 2 times what? 99? 99 is 3 times 33. So I have 2 times 3 times 33. 33 is 3 times 11. So the top can actually break down 2 times 3 times 3 times 11. 306, let's see, 3 goes into that, 102. 102 is 2 and 51. And remember, 51 was 3 times 17. So I have 2 times 2 times 3 times 17. So I can get rid of my 3's and my 2's. So I'm left with 33 over, what, 10, 20, 34. 33 over 34. Okay, wait a minute. I think I did something wrong there. Oh, that should have been a 3, not a 2. 3 times 102. Right, this should have been a 3. Sorry. So, yeah, that's a 3, not a 2. All right, so this 2 still cancels with this 2, and these 3's cancel. Okay, so I end up with 11 over 17. All right, and what's the last one? So 2xy, and I'll write it as 2y's. 6 is what, 2 times 3? YZ. So I can get rid of one of the y's. I can get rid of the 2's. So I have xy on top and 3z on the bottom. Okay. So it's just a kind of a quick way of seeing the factors. So instead of dividing out, you can just cancel the common factors. Might help you break things down a little quicker, especially if you're dealing with bigger numbers and variables. Okay. So yeah, okay. So some applications of simplifying fractions. Lisa and Lynette are taking online courses. Lisa has completed 14 out of 16 assignments in her course, and Annette has completed 15 out of 24 assignments in her course. So remember, there's 2 different courses here. What fractional part of her course, of her total number of assignments, did each woman complete? And which woman has completed more of her course? So Lisa completed 14 out of 16, and Lynette 15 out of 24. So if we reduce the 14 out of 16, we have 7/8. The 15 out of 24, we have 5/8. So 7/8 is actually more than 5/8, right? All you have to do is compare the numerators when the denominators are the same. So we see Lisa has completed more of her course than Lynette has. Lisa, you have a pre-mixed heparin sodium solution. The concentration is 25,000 units in 500 milliliters. What is an equivalent concentration? All we have to do is reduce the fraction. 25,000 units over 500 milliliters. Cancel a few zeros. We have 250 over 5. They're both divisible by 5, right? 5 is common to both. Cancel it. We have 50 units per milliliter. Okay, so of the 88 constellations that have been seen in the night sky, 13 or 12 are associated with astrological horoscopes. The names of as many as 36 constellations are associated with animals or mythical creatures. So of the 88 constellations, what fraction is associated with horoscopes? What fraction is associated with mythical creatures? So again, the total is 88. 12 of the 88 are associated with horoscopes. 36 of the 88 are associated with mythical creatures. So if we wrote those as fractions, we have 12 of 88, which reduces, that's 4, so that would be 3 and 22. Because basically what I did, I got a 4 out of each. 12 is 4 times 3. 88 is 4 times 22. So I can cancel the 4s and I get 3 over 22. And 36 out of the 88 are associated with mythical creatures. So 4 again, right? 36 is 4 times 9, 4 times 22. Get rid of the 9s, or the 4s, I have 9 over 22. Okay, so the second one, Jonathan and Jared both sold raffle tickets for a fundraiser. Jonathan sold 25 of his 35. Gerald sold 24 of his 28. So first of all, which fraction represents each amount of sales, and which person sold the greater number of tickets? So Jonathan is 25 out of 35, which reduces to 5/7. And Jared was 24 out of 28, which reduces to, let's see, 24, half would be 12 over 14, which again would be 6 over 7. So you have 5/7 and 6/7. Jared actually sold more. Okay, so section 4.3, multiplication and division of fractions. Okay, so 4.3, multiplication and division of fractions. So multiplying fractions is pretty easy. I think it's probably the easiest of the operations that you'll perform on fractions. All you do is multiply across the top and across the bottom, and then reduce if possible. So one thing I will say is write out the multiplication before you actually multiply. This way you can do some reducing before you even multiply, and it will save you reducing at the end, and it'll make your numbers smaller. So if we have -7/12 times 11, remember this is 11 over 1. If we're multiplying a negative times a positive, it remains negative. So multiply across the top, 7 times 11 is 77, 12 times 1 is 12. Then if you could reduce it, reduce it. If not, then you are in lowest terms. So 77 over 12 does not reduce, so we are in lowest terms. So this will turn into a mixed number, but remember, turning something into a mixed number is not reducing it. It's changing the form of the number. Now, if you've started out with mixed numbers, change them to improper fractions. This way you have your tops and your bottoms. So 5 times 2 is 10, plus 3 is 13, and it remains negative, so it'll be -13 over 5, and we have -1/2. Remember, a negative times a negative is a positive. 13 times 1 is 13, 5 times 2 is 10. So if we look at these two fractions, we have some variables involved. So 6a squared b to the third, 6 is like 2 times 3. A squared times b to the third is AABBB. So this, I wrote out the multiplication, but I didn't actually multiply yet. And I did the same thing at the bottom. I expanded the 4 into the 2 2's, and I wrote A times B or B times A. This way you see all your variables and you can cross out the matching pairs. Same thing with your factors. So we end up with a 3 and a 2, 3 on top, 2 on the bottom, an A and 2 B's on top, and no letters on the bottom. So then I can rewrite that BB as B squared. Okay, so before we learn how to divide, we have to learn what the reciprocal is. If you don't already know, the reciprocal of a number is basically interchanging the numerator and the denominator. Okay, so we're going to take a fraction and flip it over. That's actually called taking the reciprocal of the fraction. So the reciprocal of -6/7 would be -7/6. This reciprocal of 2, remember this is the same as 2/1, would be 1/2. And characteristic about reciprocals, if you multiply a number by its reciprocal, you're going to end up with a +1, right? So 3 1/3 are reciprocals. I multiply them, I end up with the +1, because I'd end up with 3/3, which is 1. -3, the reciprocal would be -1/3. And again, if I multiply them, I end up with the +1. So that's a characteristic about reciprocals. If you multiply 2 reciprocals, you're going to get a +1. So therefore, we need a reciprocal when we divide fractions. In order to divide 2 fractions, we multiply the dividend, which is the first fraction, by the reciprocal of the divisor, which is the second fraction. So you can think of the dividend as the fraction being divided, and the divisor as the fraction doing the dividing. So here you have A over B divided by C over D. A over B is being divided. C over D is doing the dividing. So we would change our division to multiplication, and we would take our divisor and flip it. And then we just multiply. So 9/7 divided by 5/2 would be turned into 9/7 times 2/5. Multiply, and you get 18/35. So a complex fraction is actually a division problem. A complex fraction is a fraction over a fraction, or a fraction within a fraction. So a complex fraction can be as simple as one fraction, say 1/2/3, or it could be 4/5/3, or it could be 4/3 over 2/7. So a complex fraction is a fraction within a fraction, and by that I mean it's a fraction that has either another fraction as its numerator, denominator, or both. And these are all just division problems. So if we look at the first one, 1/2/3. 3 is doing the dividing, that's your divisor. And remember, 3 is the same as 3/1. So 1/2/3 is the same as 1/2 divided by 3, or 3/1. So we change that to 1/2 times 1/3, right? Change it, flip it. So that gives us 1/6. The other one, 4/5/3. Whole number of 4/5/3 is the same as 4 divided by 5/3. 4 is the same as 4/1, so we could say 4/1 times the reciprocal, which would be 3/5. So that gives us 12/5. And then the last one was what? 4/3 over 2/7. 4/3 over 2/7 is the same as 4/3 divided by 2/7. Keep it, change it, flip it. So we have 28 over 6, which now that needs reduced, but I could have done the reduction before I even multiplied, right? 2 goes into 2 once, 2 goes into 4 twice. So the 2 times 7 would be 14 over 3. And notice 28 over 6 reduces to 14 over 3. Okay, so the one on the slide, it looks a little intimidating, but let's break it down. So we have our top. We have 6ab squared. We're going to write it as 6abb. And the bottom 7df. So it's over another fraction, which means it's being divided by that. So I'm just going to write it as a division problem. And the top of this fraction is 21 or 2AA over 21d squared f. So d squared is ddf. So I'm going to keep it, the first one, keep the first. Change the operation, and then I'm going to flip the second one, 21 ddf over 2aa. So I'm going to start canceling. This a and this a. This d and this d. Let's see, any b's on the bottom? No. Oh, the f's cancel. Okay. So I've taken care of all my variables. So I'm just going to write this out again, just to illustrate. So the next thing I'm going to do, I'm not going to multiply. Not yet, because I see I can do some reduction. 7 goes into 7 once, 7 goes into 21 3 times. 2 goes into 2 once, 2 goes into 6 3 times. So I have 3bb times 3d over a. So that would give me, if I multiply across the top, 9bb is b squared d over a. Okay, so there's multiple ways you can do this canceling. It's up to you the way you want to do it, if you want to do it. You didn't have to. You could have multiplied this all out to begin with and then done your reductions at the end. But sometimes when you do it inside, it saves you some time and makes your numbers smaller and easier to work with. Okay, so let's look at these. So let's see, 1/2 times 5/7. There's nothing that'll cancel between the top and bottom, right? There's no common factors. Negative times a positive is negative. 1 times 5 is 5. 2 times 7 is 14. So the next one, notice I have an x in the top and an x in the bottom. Those cancel, right? So I have 4xy over 15 times 3 over x. These x's cancel, and I can also cancel this 3 with the 3 and the 15, right? 15 is 3 times 5. If I wrote it as 3 times 5, I'm canceling those 3's. So I have 4y on top and 5 on the bottom because I got rid of that x. Okay, so now we have a division problem. 2 over 15 divide. So I'm going to keep this. I'm going to change the operation and I'm going to flip the second fraction. Okay, so I know 15 and 12 have a common 3, right? If I take a 3 out of each, I get 4 here and 5 here. So I have 2 times 4, 5 times 5, 8/25. And the bottom one, we have a complex fraction. We have 4x over 15 divided by 2x. And if you want to place it over 1, if it helps you to see that 1, that's fine. So I keep this fraction. I change the operation, and I flip the second fraction. So before I even multiply, I'm going to get rid of my x's, and I'm going to get rid of my 2's. This 2 and the 2 that's in the 4. Then I have 2 times 1 on top and 15 on the bottom. Okay. So don't be scared when you see a mixed or a complex fraction like this. Rewrite it as a division problem. It looks a little less intimidating when you rewrite it. Okay, so some applications of division of fractions. So a lab tech has 1 3/4 liters of alcohol. If she needs smaller samples of that, if she needs to make 1/8 liter portions of this 1 3/4 liters, how many can she prepare? So if we are taking this larger amount and making smaller portions, we are dividing. So 1 3/4 divided by 1/8. But 1 3/4, we're going to turn that into an improper fraction. 4 times 1 plus 3 is 7. So I have 7/4 divided by 1/8. So I keep the first fraction, change the operation. From division to multiplication, I flip the second fraction. So 7/4 divided by 1/8 becomes 7/4 times 8 over 1. And this 4 and this 8 cancel, right? This 4 becomes a 1, this 8 becomes a 2. 7 times 2 is 14. If a bottle of medication holds 250 milliliters, and you have to administer 2.5 milliliter doses, how many doses can you get out of that bottle? Again, we're making smaller portions from a larger portion, so we're dividing. 250 divided by 2.5 becomes 5 halves. So we change it to a multiplication of the reciprocal. 250 times 2 over 5. 5 goes into 5 once, 5 goes into 250 50 times. So you have 50 times 2, which is 100. Okay, so a couple more application problems. Okay, so if 1 cup is 1/16 of a gallon, how many cups of orange juice can be filled from 3/2 of a gallon? So we have 3/2 of a gallon, and we're pouring it into cups, and each cup holds a 1/16. Again, we have a larger portion, and we're creating smaller portions. We're dividing. So we have 3/2, and we want to know how many smaller 1/16 we can make from it. So we take 3/2 and divide by 1/16. Which is the same as 3/2 times 16 over 1. But before I multiply, I'm going to get rid of the 2's, right? There's a 2 times 8 makes 16, so I'm just canceling my 2's. 3 times 8 is 24. Okay, so the next one's a little bit different. In a certain sample of individuals, 2/5 are known to have blood type O. Of the individuals, so of those 2/5, a fourth of those 2/5 are Rh negative. What fraction has O negative blood? So we're trying to find a fourth of 2/5. So now we're actually cutting this 2/5 into fourths portions. So you could think of it as division. So let me draw a picture. So if this is our people, we have 1, 2, 3, 4. Let me make it a little bit bigger. Okay. So this is our whole sample of people. And we have a fifth, a fifth, a fifth, and a fifth, and a fifth. Then we take 2 of these fifths and we cut these into smaller fourths. 1, 2, 3, 4. Okay, so I know they don't look equal, but that's fine. So we're looking for a fourth of a fifth, a fourth of 2/5. So you can think of it as 2/5, not 2/3, divided by 4. So remember, because these are fractions, when you divide, you flip it and multiply. So it's actually 2/5 times 1/4. So 1/4 of 2/5, or 2/5 of 1/4. If we cancel these 2's, 1/10. So 1/10 of the sample has has O negative blood. Okay, so I mean, even though it's division, when we just say, when you take a fractional amount of something, you're multiplying, because you're going to divide it, but then you're taking some of it. So anytime you see the word of, you should think multiplication. 2/5 of something or a fourth of something, we're going to multiply. So a fourth of 2/5, we multiply a fourth times 2/5, we end up at 1/10. You can think of it again as, we'll get into this later, but fractions and decimals are closely related. A fourth of something is the same as 25% of something. So you can kind of think of it as multiplying by a percent. But we'll talk more about that later. Just know that the word of indicates multiplication. Okay, so least common multiple. So first you have to understand what a multiple is. Multiple just means to multiply. The multiples of 2. First multiple is 2. Second multiple, third multiple would be 3 times 2. Fourth multiple would be 4 times 2, so on and so forth. So you're just multiplying 2, 4, 6, 8, 10. You can think of it as counting by 2's. You're multiplying 2. Multiples of 3, 3, 6, 9, 12, 15, so on and so forth. So common multiples are multiples that are common. So if we look at 2 and 3, a common multiple is right here, 6. But if we kept going with the 2, another common multiple is 12. So right now we're showing 2 multiples that are common. Well, the least common is the smallest common. So 6 is the smallest common multiple of 2 and 3. The least common multiple is the smallest whole number that's a multiple of any given number. Here we look at 4 and 8, do our multiples. We see 8 and 16 are both common, but 8 is a smaller. So the least common multiple is the product of unique prime factors. So prime factorization is another way to find least common multiple, which you'll see later. Least common multiple of denominators of 2 fractions is the lowest common denominator. We'll talk more about that later. So to find the least common multiple of 2 numbers, write them in their prime factored form. Then you need each factor. So if we look at 15, break it down to its primes. The primes that make up 15 are 3 and 5. We look at 18, break it down to its primes. The primes that make up 18 are 2 and 3. So we need each factor. We need a 3, a 5, and 2. Because that's all we see up here, 3s, 5s, and 2s. So we need 3, 5, and 2. But 3 has an exponent, so we need that exponent as well. We need the highest exponent. So if your number, say you had a different number over here and it had a 3 squared and this had a 3 to the 3rd power, you would need the exponent of 3. You need the highest exponent. So let's look at these two numbers. Oops. I want to know the multiples, the least common multiple of 180A and 126B. So I break them down to their primes. The primes of 180A are 25233A. So that's 2 squared times 5 times 3 squared times A. The primes of 126B are 2 times 3 squared times 7 times B. So my least common multiple must contain a 2, a 5, a 3, an A. I already got 2, 3, a 7, and a B. Because those are all the factors that you see. Now I have to pull exponents. This 2 has an exponent of 2. This has no exponent, so I need that too. The 3's both have the same exponent, so I just need that exponent. If 1, 3 had a bigger exponent, I would need the bigger of the 2 exponents. So this is my least common multiple. If I multiply this out, that's what, 4 times 5 times 9 times 7. This is 20, and that's 63. So it'd be, 0. 0, 6, 1,260, but don't forget your letters, AB. So the least common multiple between, what was it? Oh, hold on one second. Okay, so the least common multiple of 180A and 126B is 1,260AB. And we can do the same down here. So let's look at these. So if we take 12 x squared yz, and we break it down to its primes, 12, remember, is 3 times 4, and 4 is 2 times 2. So we have 3, 2, 2, or you could write it as 2 squared. Then you have x squared, y, and z. 18, you can think of it as 2 times 9, right? 2 times 9, and 9 is 3 times 3. Here. Oh, let me do it on top. How about that? So for the 12, we have 2 times 2 times 3 times x squared times y times z, which you don't need those multiplications between your letters or your letters and your number. That's understood to be multiplication. And the 18, we have 2 times 9, which is 3 times 3, w squared x, y. So the least common multiple of the numbers, we need 2's and 3's, right? We need a 2 and we need a 3. Exponent-wise, this would be 2 squared. This would be 3 squared, so we need a square on each of them. Letter-wise, we need the letters to their highest powers. So we need x, y, z, and w. X, y, z, and w, and we need the highest powers. Just like with the numbers, you need the highest powers. With the letter, you need the highest. So x, we need the square, and w, we need the square. If we multiply that out, we have 4 times 9, which is 36, x squared, y, z, w squared. Which normally we'll write the letters in alphabetical order, but it doesn't matter. It's not gonna be wrong if they're not in alphabetical order. So the least common multiple between 12x squared yz and 18w squared xz is 36x squared yz w squared. Okay, I see here I wrote it alphabetically. It doesn't matter. And actually that is where we ended in class, so I will end there. And your quiz will be Monday. The quiz, though, only goes up to section 4.3. So this stuff we're doing here, remember, we started 4.4. 4.3. Right here we started 4.4. So the least common multiple stuff won't be on your quiz. Okay, so if you have any questions, email me. We could set up a Zoom session, tutoring session, over the weekend if you like. Just let me know. So have a good day.